Thank you. So yeah, this is about quantum computing. So quantum computing is not new. It has been studied in the 80s and 90s, but most of the research so far have been theoretical and considering millions of qubits and hours of computing. We had a very great talk by Jens Basberg earlier today. We were talking about how today we start to have actual quantum computers, and that's what's new. But these actual quantum computers are much more modest than what we used to consider in the prior years. So now we have tens to up to 100 of qubits, and they're very noisy. They're imperfect. So we have to do with what we have today, and that's important to just not wait until we have bigger machines, because we may not even get them if we don't. Like for now, we get a lot of money, but if there's not any return on modest size problems, then we may not get any more investment for the next 20 or 30 years. So what we're interested in is how to program this first generation of quantum computers and how to compile quantum algorithms expressed as quantum circuits down to the bare metal programs running on the current generation of quantum computers made of superconducting circuits. So this is just compiler development, but this has new features, there are new constraints, and the intermediate representation are different. So we need to find counterparts of the standard optimization like instruction scheduling, register allocation, which we'll consider now. So register allocation, or its equivalent in quantum, that is qubit allocation, is how you map the variables in your program to the physical resources, the registers or qubits on the computer. So we have a program with variables of qubits, and we need to find a set of physical qubits that obey the constraints. And it's important to minimize the number of operations and the execution time, because the more operations you do and the longer you wait, the much worthless your result is, or the bigger chance that you get a worthless result because every operation introduces some noise. So I'll first discuss how we model the qubit allocation problem and then propose an algorithm to solve it. So what do we get as an input of our compiler? So the most popular abstraction for programming quantum computers at the moment is quantum circuits. So a quantum circuit operates on variables or qubits and performs so-called gates that are like instructions that can affect either a single qubit or multiple qubits. And eventually, we need to get back to the classical world. So we need to measure the qubits to turn them into bits. And the main difference from classical circuits is that we cannot duplicate qubits. So we cannot connect one output to multiple inputs. So it's a very restricted form for a data flow graph. So in this talk, we'll consider the central part of the circuit between all the initializations and all the measurements. So we have a fixed number of qubits. And we assume that the circuit was decomposed by a front-end compiler to just a set of single qubit gates that we'll essentially ignore here, and 2 qubit and the particular 2-qubit gate that we call the control NOT. So this program is expressed typically in a dialect of the CASM language, which is an assembly level or intermediate representation for quantum programs. And our target is the most popular technology at the moment, which is superconducting qubit quantum computer. So these are the tiny chips that sit in the middle of a huge refrigerator. And the qubits are these squares. Here we have 5 qubits, and they're connected to the outside, so we can control them, like make operations and measure them. And they are also connected to each other through resonators, so they can perform CNOT gates with each other. However, it is not a complete graph. They are not all connected to all qubits. So in these cases, we have a butterfly topology and a ladder topologies for these 2 examples. So qubit allocation has to take an arbitrary circuit as input, from which we can compute the dependencies. So in this example, qubit 0, logical qubit 0 communicates with logical qubit 1, so we add an edge to the dependency graph, like as usual. And now we want to embed this graph on the physical connectivity graph of the computer. And that's an NP-complete problem. That's the well-known subgraph isomorphism problem. And that's NP-complete. However, even if we were able to solve this problem, the answer will usually be useless because the answer is usually no. There's no mapping from the dependency graph of a complete program to our computer. So we need to transform the circuit in order to make it fit the topology of the machine. And the transformations we can make are, so we consider 2 kinds of transformations. So there's this somehow counterintuitive operation that allows to reverse the direction of a control NOT operation by inserting like 2 levels of Hadamard gates. And that way we can reverse the dependencies at the cost of extra gates. And we can also swap 2 qubits. So we cannot duplicate qubits, but we can move them around by swapping with what's essentially the quantum equivalent of the trick of doing 3 XORs to swap 2 variables. So now from this theoretical tools, how can we solve or approximate the qubit allocation problem? So we'll propose a 3-step algorithm to find a good solution to qubit allocation. So the first step is to use subgraph isomorphism to solve smaller instances of the circuit. So we want to break our circuit into multiple partitions, where each partition can admit a mapping to the physical circuit. So in this example, we have 6 physical qubits, A to F, in a 8 topology. And we start by allocating our qubits. So for instance, we have a dependency from 1 to 2. So we can allocate them to C and E, and so on with dependencies 4, 5, 3, 5, 2, 4. And then we want to add an extra gate between 1 and 3. But there's no link between 1 and 3. And there's no solution even if we change the mapping, because there's no diagonal in our connectivity graph. So we start from a new partition, and we keep going and create a new partition every time we cannot find a solution. So since the problem is of subgraph isomorphism is NP complete, we use an approximation. So we bound the number of solutions to keep it tractable. And also we built incrementally the solutions. So for each partition, we end up with a set of solutions. Now the second step is how we can pick one solution within each partition that minimizes the amount of work we need to do to go from one solution, from one partition to the other partition. So by definition, we have different solutions, so we will need to swap one or more qubits to go from one solution to the other. So in this example, we can go from this mapping to that one by swapping qubit 2 and 3. And then to the second mapping to the third one by swapping qubit 1 and 3. So this problem of picking one solution in each partition can be solved with dynamic programming, assuming that we can estimate the cost of swaps to go from one mapping to the other. And finally, we need to generate the code for the swaps between each pair of partitions. So while the subgraph isomorphism problem is well studied, this particular problem is very recently studied. It's the token swapping problem. And quite recently, there was a 4 approximation algorithm proposed to as a heuristic to solve this problem. So this complexity is cubic with the number of qubits here, or tokens. So we reuse this algorithm with a small adaptation to take into account the fact that uninitialized qubits are set, or qubits are initialized originally to 0, and we don't need to swap zeros with zeros. They're all zeros. Also, we use a result from this work to compute easily an upper bound for the number of swaps needed to go from one mapping to the other that we can use in the dynamic programming phase. So finally, combining these 3 steps, we get an algorithm that's very competitive. So here we plot like a large number of real benchmarks, like real for the current kind of programs we have on quantum computers. And we normalize it to the cost, that is the number of operations that we add, weighted by the cost of each operation. So one is our algorithm, bounding mapping tree. And in most cases, it gives the lowest cost. And for the subgraph isomorphism phase, we can tune the aggressivity of the heuristic. So we can derive also a faster version that's 3 times faster and is within 2% of the result. So we presented a way to formulate the qubit allocation problem as a combination of subgraph isomorphism and token swapping. And this allows us to derive an actual algorithm to find a good solution with bounded search for the subgraph isomorphism problem, then doing dynamic programming to assemble the solutions and doing token swapping to actually generate the code. And using the parameterization, we were able to scale it to about 100 qubits. Then scaling to larger computers will require tuning the heuristics, but I'm quite confident that we can use the same framework with better heuristics to scale further. Also, it would be interesting to consider not just static circuits, but things like CFGs with when we have loops with classical control flow. That's something we can do in a hardware. And if you have quantum programs that you need their qubit allocated, you can play with our algorithms and also the other algorithm on our website. So thank you.
Hello, thank you for the interesting talk. So I asked this question at the quantum computing talk earlier today, but I'm curious what you think about the possibility of using quantum computers for solving the qubit allocation problem in the future when quantum computers are actually capable of larger, interesting computations.
So do you mean how does it scale with bigger computers?
No, I'm interested, like, could you use a quantum computer to solve this problem efficiently?
Yeah. So there are two. First, that's a very interesting question. I think we can express this as a quantum computing problem, but what we really want is to solve qubit allocation on a quantum computer that has fewer qubits, or at most the same number of qubits than the problem we want to solve. And that, I think that's quite challenging at the moment.
Very good talk. Let me ask about the first step. How many partitions do you end up with for your benchmarks?
So these are fairly small benchmarks because they are like near-term quantum computers.
Yep.
So I don't have the numbers at hand, but these are in the tens to maybe 100.
Okay, I see. Okay. No, thanks.
I have a question. So in your approach here of using the partitioning, did it give you any hints for how you might use similar techniques for other parts of the quantum compilation tool chain, like maybe optimization or analysis of some sort?
So yes, there are. I don't know if this would be the answer of your question, but there's also the problem of the current of instruction scheduling and instruction selection, because when we insert swaps, we also kind of serialize the execution. So depending on where if we move around, we have some degree of freedom here. So if we do gates, like gate scheduling before or after, that may. So currently we take into account the fact that we can choose which. Like for instance, if we cannot add this to the partition, maybe there's that one that we could and schedule it earlier. But in the general case, that there are like interplays, and that's something we need to study.
Any other questions? Okay, so now there's the awards and the business meeting, which I think is downstairs in the other room. Let's thank the speaker one more time.
Thank you.